As we all know, air quality is a critical concern which affects multiple domains. However, there are still challenges that persist in this research area, such as modeling of complex air quality dynamics, the problem of data sparsity, lack of interpretable models, and even prediction of sudden changes. All in all, the related work in this domain fall under two main paradigms, physics-based and data-driven. Physics-based models are inspired by atmospheric science, whereas data-driven models utilize historical pollution data to learn complex relationships. However, both of these modeling paradigms have their own limitations. Physics-based models are often employed on larger spatial scales, restricting fine-grained predictions, and they are too resource-intensive. On the other hand, data-driven models, despite their promising outcomes, require extensive data to accurate predictions, and also lack of physical constraints limit their generalizability and robustness as well as interpretability. Alleviating these limitations of both the paradigms, we introduce AirFiNet, a novel hybrid deep learning approach which uses underlying physics related to air particle movement as domain knowledge. So this is the model architecture of AirFiNet, which consists of three main components. Initially, we have a gated recurrent unit as our RNN encoder, which extracts temporal information from the historical data. Based on the final hidden states of the GRU, we determine an initial state ZT node. Secondly, we have the GNN-based differential equation network that transcends the traditional modeling by embedding physical constraints within a neural network using several mathematical derivations. Within this model, the diffusion model is processed by graph convolution using a graph Laplacian calculated by considering distance as the edge weights. On the other hand, for the advection process, which accounts for the transportation via wind, we consider wind vectors into the model, employing a modified graph Laplacian reflecting the wind transport dynamics. To consider both of these processes simultaneously, we employ a gated fusion mechanism, which results in an advection diffusion differential equation denoted by Fg. Considering Fg and ZT node and including them in an ODE solver, we generate the future states, and we use a simple decoder to decode these future states and generate PM2.5 predictions. So we conduct experiments on two real-world datasets, Beijing and Shenzhen, and over both these datasets across all time horizon, our models perform the best. Then in prediction of sudden changes as well, our model outperforms all the other baselines by a significant margin. We also wanted to see how well our model generalizes to unseen data. As you can see, AirFiNet outperforms all the other baselines by a significant margin of about 8% in all time horizons. So that means our model generalizes effectively and yield precise predictions, particularly in scenarios with limited data. Then we wanted to assess our model qualitatively, and we visualize the predicted PM2.5 concentration together with the wind direction. As you can see in both the scenarios, the PM2.5 particles move in the direction of the wind and join the PM2.5 cloud. In terms of interpretability with regards to diffusion, we visualize the magnitude of diffusion and the PM2.5 concentration, and as you can see, the diffusion of particles from station 3 is relatively higher to stations with lower concentration, and it's low to stations with higher concentrations. Therefore, AirFiNet successfully captures the underlying physics and yield precise predictions with a physical meaning. All in all, to conclude, we propose a novel physics-guided neural network known as AirFiNet, which integrates the fundamental physical processes into a deep learning framework. And our experiments on two real-world datasets shows that our model performs the best in different testing scenarios, and our case study further validates the model's capability to generate precise prediction that can be interpreted within a physical context. Thank you.